we have a demonstration prototype. Here we have a demonstration prototype. We have a prime mover, we have a generator, we have a generator coil here, and this prototype has a conventional generator coil that will supply power to this light bulb. And when it does that, we will see the effects of the counter electromagnetic torque. Okay? As soon as we place the generator on load, the prime mover will respond by consuming additional electrical power, which means that it's delivering the prime mover, the motor will be adding mechanical power to the drive shaft. Okay? So this is where the cost of, this is where the 24,000 trillion cost comes from. It's the counter electromagnetic torque that the generator coil produces that requires additional input power to be supplied by whatever's driving the generator, whether it's wind, steam, you name it. And what we'll also see is we'll see the speed of the system will decrease, the input will go up, and we will deliver about 10 watts to this load. Okay? Then we will use the Regenex coil that's also in the same coil configuration to reverse the generator armature reaction and produce a complementary electromagnetic torque which causes the speed to go up and causes the consumption in the prime mover to go down to below the level, to below what was required at idle. It's very important that we understand what's happening at idle, because at idle, the drive shaft, the power in the drive shaft, right now this drive shaft is at static equilibrium. There's no torque on it. The power in the drive shaft is, the mechanical power in the drive shaft is the torque times the speed. At static equilibrium, the torque is 0, therefore the power in the drive shaft is 0. At rotational equilibrium, when it's rotating at a steady state speed, is where we start the demo. The net torque in the drive shaft is also 0, so the power in the drive shaft is 0. Okay? So when the conventional generator is placed on load, the counter torque will rob the drive shaft of power, and we'll see a response in our prime mover and our speed. When the Regenex generator is placed on load, the prime mover will be consuming less power than it was at idle. And what I'll be doing as well is showing you the load current sine wave for the conventional coil and the load current sine wave for the Regenex coil. And this is where the acceleration comes from. I'm not going to get into any more detail than that, but I want you to have a slight idea of what the innovation is and how things go, and then we'll go to the other coils. So right now, we are at a steady state speed of 3,489 RPM. We're at rotational equilibrium. The prime mover is consuming 234, let's say 246 watts. And when I place the conventional coil on load, we'll see the input go up here, and we'll see the speed go down. So the prime mover is consuming whatever we take from our conventional coil in terms of watts. We have to replace that into the prime mover. And when we use the Regen-X coil, now our prime mover is consuming less power than it was at idle, and we are delivering more power to the load than we were in conventional load. The purple sine wave is the load current sine wave for the conventional load current, and the green sine wave is the sine wave for the Regen-X coil. Can you see this, Jeff? Yep. Yes. So I'm going to put it back onto idle again, because I want you guys to understand what's going on a little more. So 3495 is our steady state speed, and our prime mover is consuming 200 and bouncing around at about 240 watts. So when I place the conventional coil on load, this number will increase and this number will go down, which means that the counter torque that's produced from the conventional coil is working against the rotation of the system. Is that clear? Does everybody see that? And then when the Regen-X coil is placed on load, the speed goes up, and this number goes lower than what we needed at idle. So is that clear to everybody? Okay. This is kind of boring, I understand, but I want you to get the same sense of what Paul would have seen last week. So now our prime mover is consuming less power than it was consuming at idle. It's delivering less mechanical power to the drive shaft, less mechanical power than it was delivering at idle. That we are generating, we're generating more power to the load in regenerative acceleration mode with the Regen-X generator than we were doing with just the conventional generator coil. So in electricity generation, when the generator is placed on load, the counter torque produced by the generator coil requires additional mechanical power to be supplied by the prime mover in the drive shaft to keep the generator turning, or the generator will completely stall the system if you take enough power from the generator. The RegenX technology, on the other hand, says that requirement is no longer necessary. When we place the RegenX generator, when the RegenX generator delivers output power to the grid, to the load, to the batteries in an EV, there is no additional mechanical power that needs to be supplied to the drive shaft. And in fact, we are using the same magnetic fields that you felt in this generator that we're creating counter torque to produce a complementary electromagnetic torque, and this is why we get system acceleration. So in the development of the technology, in the development of the RegenX generator coil, in 2008, we started with basically this dual coil approach with a conventional coil and a RegenX coil on the inside, which is what we have here. In 2010, this two-coil approach was integrated into a single coil, and then the technology improved from 2010, where we were delivering about 1 amp per coil, to 2018, where we now have commercially manufactured coils that this coil will deliver between 10 and 20 amps of current. This coil will deliver 60 amps of current, and this coil, this commercially manufactured coil, will deliver in excess of 100 amps of current. So the process that we applied in the development of the technology was to, number one, ensure that we could scale up from 1 amp to 10 to 20 amps to 60 to 100. That gives us the indication that as we scale up to 100 amps or more, as we get into bigger and bigger generators, the design of the coil scales up accordingly. And that's important because if we're getting into manufacturing, we want to be sure that as we scale up the coils, we're not going to lose the effect at some point down the road. And we basically established that doesn't occur. So the next part of the demonstration